you learn about to derive the equations for maximum effective aperture, derive the equation for maximum effective aperture and directivity for a lambda by 2 antenna, or else we can also call it as a for a off wave antenna. And finally, or is the other way, what we can write is show that the maximum effective aperture is 0.13 lambda square and directivity is 1.64 for a lambda by 2 antenna. So to derive the maximum effective aperture, or as to know the maximum effective aperture for a lambda by 2 antenna, first of all we need to know what is a lambda by 2 antenna. As the name suggests, a lambda by 2 antenna is an antenna where the total length of the antenna is half of its wavelength. So the lambda by 2 antenna is also called as off wave antenna. So lambda by 2 antenna is also called as a off wave antenna or as off wave dipole antenna. So for this, let us consider the diagram. Let us consider a lambda by 2 antenna. This is a lambda by 2 antenna. Even this is a something like a short dipole antenna because the length of the antenna will be less. So let us consider a lambda by 2 antenna placed along its y-axis with center at the origin O. So as the antenna is placed in XYZ coordinate system, so this is X coordinate, this is the Y coordinate, and this is the Z coordinate. And as we are placing the antenna at the center, the field distribution will be just opposite to it. This is the entire field which we have. And here also once again this is the total area and this is the elemental area dy. And even here we consider the resultant field, which is the resultant electric field E. That is E is equal to E naught into cos of omega t. E is equal to the total resultant field E naught into cos of omega t, and this is the maximum radiation which is just opposite to the direction of the antenna. So we just go with the same equations, that is to consider as we are considering a lambda by 2 antenna, the resultant field is E is equal to E naught into cos omega t, and next the same step, that is E is equal to E naught into cos 2 pi by lambda, cos 2 pi by lambda. And when you are assuming the elemental length dy, the potential difference across this is given as dV is equal to Ey into dy, which is the elemental potential difference. So therefore the potential difference is V is equal to integral of dV, and as it is the elemental surface, it is integral Ey into dy. And we can express the value in terms of total resultant electric field, which will be taken as the integrated value. So V is equal to E naught into integral minus lambda by 4 to raised to the power lambda by 4 cos 2 pi by lambda into y into dy. Here we take it as lambda by 4 because the antenna is a lambda by 2 antenna. When we divide this lambda by 2 antenna into two different parts, then it acts as lambda by 4 antenna. That is, one off wave section is equal to two quarter wave sections. Please understand the concept. One off wave section, this is one complete semicircle. This is the total value lambda by 2. And when I divide this, then it is two quarter wave sections. That's why it is lambda by 4, lambda by 4. That's the purpose why we are writing the integral, that is minus lambda by 4 to plus lambda by 4. Now the final equation is V is equal to E naught into lambda divided by 5 volts. This is the voltage. And let me take this as equation number 1. The total resultant voltage is E naught into pi E naught into lambda divided by pi. Let us consider this as equation number 1. And always the radiation resistance for a lambda by 2 antenna is 73 ohms. This is once again a value which is known, and in further sessions of the subject you will be deriving why the radiation resistance of the lambda by 2 antenna is 73 ohms. But as of now, we just need to understand and consider that the radiation resistance of the lambda by 2 antenna is 73 ohms. Next, the maximum power radiated at the reception of the antenna, that is maximum power density for maximum power reception. P is equal to E naught square divided by 120 pi. So let this be equation number 3. All these three equations are very much important. Next, the maximum effective aperture for an antenna can be derived by the equation, that is AEM is equal to V square divided by 4 into P into R. Now, already by the equation number 1, 2 and 3, we know the values for V, RR radiation resistance and also P. Let me consider this as equation number 4. Now, by substituting the values of equation 1, 2 and 3 in equation 4, we get the final value of maximum effective aperture for the lambda by 2 antenna. So, now substitute the values of equation 1, 2 and 3 in equation 4. So, it will be AEM is equal to E naught into lambda divided by pi whole square divided by 4 into E naught square divided by 120 pi into 73. So for the E naught square and E naught square will get cancelled. Pi and pi will get cancelled. And 4 divided by 120 and that multiplied by 73, we get the final equations. So next for the 4 and 120 we can divide and that is multiplied by 73. So finally the equation will be AEM is equal to 30 divided by 4 ones are 4 30s are 120. So it is 30 divided by 73 pi into lambda square. Now let us do this further substitution or a simplification, that is AEM is equal to 30 by 73 into pi, that is 3.14 lambda square. Now finally we get 30 divided by 73 into 3.14 will be 0.13 and lambda square we cannot do anything as we are obtaining the equation for AM in terms of lambda. So the final value for maximum effective aperture for a lambda by 2 antenna is 0.13 lambda square. So this is the equation for maximum effective aperture of a lambda by 2 antenna. It is 0.13 lambda square. Now with this value, let us know what is the directivity for the lambda by 2 antenna. So the directivity for T can be obtained in terms of AEM by the equation D is equal to 4 pi AE by lambda square. So now we know what is the value of AE for the lambda by 2 antenna. So let us substitute that. So it will be 4 pi into AEM, that is 0.13 lambda square divided by lambda square. Now lambda square and lambda square will cancel. Next, D is equal to 4 into 3.14 into 0.13. Now this will result as 1.64. So the directivity for a lambda by 2 antenna is 1.64. So finally we have arrived at the equation where the maximum effective aperture for a lambda by 2 antenna is 0.13 lambda square and directivity is 1.64. And in the examination, normally this question can be expected for 6 marks or 8 marks. It depends upon the paper setter. The question would be, show that the maximum effective aperture is 0.13 lambda square and directivity is 1.64 for a lambda by 2 antenna. Or is other way the question can be asked is, derive the value of directivity and the equation for maximum effective aperture for a lambda by 2 antenna. So the diagram has to be written, it has to be explained briefly and write the equations for V and write the expressions for radiation resistance and power, and the substitution steps has to be shown in detail along with the instruction. And finally, you first arrive at the equation for maximum effective aperture, that is 0.13 lambda square, And thereafter, by knowing the value of d, by making use of the equation, that is d is equal to 4 pi am by lambda square, do the substitution of aem, and finally you get the value of d as 1.64. So this is all about the derivation of maximum effective aperture and directivity for a lambda by 2 antenna, or I can also call it as off-wave dipole antenna. The off-wave dipole antenna or the lambda by 2 antenna, they are one and the same. As the total wavelength is divided by 2, we call it as off-wave antenna. Or as in mathematical terms, we can call it as lambda by 2 antenna.